Well, I've used the word system already, but what do I mean by a system? Well, maybe I can help explain it by telling you about system boundaries. A system boundary is something that's helpful because it defines the area that we want to study, or the space that we want to study. If you wanted to study, say, I don't know, an engine in your car, okay, and you're interested in what makes the engine go, well, one of the areas you may want to study is the volume above the piston that keeps changing, because that volume is where the chemical reaction takes place, where the gasoline or the fuel is burned and pushes the piston down. Now, usually our system boundary will be drawn, or we will section off our system so that we only include fluid, whatever fluid is inside the system. Now be careful, when I say fluid, you probably thought liquid, but technically a fluid can be a liquid or a gas. In fact, quite often in this class, when I say fluid, I mean a gas. So just be careful about that. Now, the boundaries that define the region to be studied, those boundaries we get to make up. We can put them wherever they want. Sometimes they are fixed boundaries, sometimes they're real, sometimes they're imaginary, sometimes those boundaries move. We have to define, as the one that's analyzing the problem, where we want those boundaries to be located, and that defines the system that we're studying. So here's an example of a fixed boundary. If you imagine if you imagine a fire extinguisher and how it would look in cross-section, there's several different components that are useful and interesting inside of it. But if we just consider the inside of the tank as the system we want to study, including whatever's inside of it, well, then that would be a fixed boundary, because we've simply defined the boundary of the system to exist at the inside wall of the tank. Moving boundaries. I mentioned a piston in your engine moving up and down in the cylinder a few minutes ago. Well, the area above the piston, those gases there, would be an appropriate system for us to study. Now, it's a little bit confusing, so I've put both these pictures on the slides right now to show you something important. A lot of times when you think of the interior of an engine, if you know what it looks like, you think about the picture you see on the left. There's a nice cutaway there. You can see the piston there that has rings. It's sort of that roundish thing. There are two smaller round things above it. Those are, well, there's actually four. You can't really see them, but they're kind of like an oval. Those are the valves that allow fluid to enter and exit. Now, I don't mean liquid, remember, I mean gas, especially in this case. Anyway, that may be what you think of. In this class, when we draw a piston cylinder device like this, we usually draw it upside down. So if you look on the right at the schematic of this, we usually assume that the piston is round. It could be really any shape, but usually we assume it's round. And then the gas above the piston is now drawn below the piston instead. So you see the system boundaries there outlined in the dotted lines. It's pretty apparent that the lower dotted line wouldn't move, right? That would be the top of the cylinder. In the left-hand side where the valves are located, but then the surface of the piston serves as one of the boundaries of the system, and of course the piston moves up and down in the cylinder. That's what makes your car go, right? So that boundary moves, and this is an example of a moving boundary. There can be imaginary boundaries and real boundaries. If you know what this is, you might recognize what's going on here. This is a two-cycle engine, which is interesting because in most engines, especially the ones in the vast majority of cars out there, it involves 4 cycles. What that means is there are 4 strokes of the piston up and down. So up, down is one complete cycle, one complete thermodynamic cycle. It's 4 strokes, because one motion of the piston from top to bottom or bottom to top is called a stroke. Anyway, what's interesting about 4-cycle engines is that they generate power in 2 revolutions of the crankshaft, but 2-cycle engines like this one generate a power stroke every single revolution of the crankshaft. And you can see the piston moving up and down in the cylinder. You can see the connecting rod that's sort of moving back and forth, and it rides on a rotating pin, and that pin is part of the crankshaft if you're not familiar with engines. What you'll notice is that air and fuel comes in on the left side of this animated image. The air is represented as the blue stuff that's coming in, and then the red-orange stuff that's sort of sprayed in, that's the fuel, and if it's a 2-cycle, hopefully some oil mixture. But you'll notice that those two mix together and generate the green substance that's below the piston, and as the piston moves down, it actually displaces some of that fuel-air mixture and pushes it up above the piston. So you see that happen right there. Hopefully the timing works. But then the piston, as it continues to move up, or as it begins to move up, compresses those gases. There's a spark plug at the top, and it fires off the reaction. It starts the reaction, the burning of the fuel. And then as the piston moves down, you see an exhaust port open and the gray sort of burned gases leave. Now we're going to study this engine more particularly. We'll study four-stroke engines in more detail. But what I want to draw your attention to is the fact that this could be a very inefficient system, because there's nothing really to keep the air-fuel mixture from just being pushed right back out of the carburetor on the left, right? There's nothing that really keeps the gases, once they're burned, from just leaving. It turns out in a two-stroke engine like this, or a two-cycle, when the gas is burned, they don't really burn all that completely. It's not a very good burn. So you want to actually scavenge them. You somehow want those gases to come back into the combustion chamber to some extent to be burned again, and that ups your efficiency of the engine, ups the power output, and it's better for the environment. It's better all the way around. So what's the magic that makes this work? What makes it happen? Well, the interesting part is the big piece on here. It's the muffler. Now, if you look at the way that this is drawn, the gray exhaust gases come out and they sort of seem to be reflected back. Why would that be? Well, if those gases are moving fast and you've got a relatively large mass in the larger area of this muffler or this exhaust pipe, what will happen is that that large mass in the larger section will act kind of like a barrier and make the exhaust gases from the most recent stroke bounce off and come back into the cylinder to get a little bit more burn time. Now, not all of it is scavenged back in, but some of it is. So the design of this muffler, tailpipe, whatever you want to call it, this section is actually really important. It may be a system that we want to study on its own besides the interesting parts of the engine. So forget the engine for a minute. We want to design this thing so that the gases coming out of the engine will actually sort of bounce back and be burned again. Now, if you think about it, this is basically a round thing, and there are some real boundaries defined by the shape of this pipe. But there are some imaginary boundaries at either end. There's an entrance on the left-hand side and an exit on the right, and we're interested in everything going on in this system. So that's an example of an imaginary and real boundary that defines a system that is interesting and useful to study so that we can increase the efficiency of the engine. Now, there are a couple different system types. We need to discuss those. There are isolated, closed, and open systems. And I'm not sure how familiar you are with each of these items. You probably have seen a thermos before on the left-hand side. And in that thermos, the idea behind it is that it needs to keep your coffee warm, right? You put your coffee in it in the morning, you go to work, and you want to have nice hot coffee by the time you get to lunch and probably even after lunch. Well, how do you make that happen? Well, obviously, if the coffee spills all over the place, that's a bad thing, right? So when we say that a system is closed, what we're saying is that there's no mass that enters or leaves the system. So, of course, we're taking the system to be the interior volume of this thermos, okay? So it's closed, meaning no mass can cross the system boundary, but that's not good enough, right? If we want to keep our coffee warm, we don't want any energy to cross the system boundary. We don't want the coffee to lose heat. And so the first system there, that thermos, should ideally be isolated. In other words, there should be no mass or energy that crosses the system boundary. Whereas if we're interested in something that's only closed, well, the image on the right is an example of a system that ideally would be closed. In other words, no mass would leak out, but energy is typically designed to cross the system boundary. And so this is an example of a solar collector. So if you think about water in your home, well, you want hot water, right? So you can take a warm shower. How do you heat the water? Well, one way you may do it is by using electricity or using a fuel, burning the fuel to heat the water. Well, that's okay, but did you know that in the summertime you can get some of that heat, if not all of it, for free? All you need is a solar collector. Now, I'm not talking about a solar panel that generates electricity. I'm talking about just taking the water and running it through some pipes on the roof of your dwelling so that the sun can beam down on it and transfer energy to the water, warming it up. And so you see the blue arrow going up on one side, that's relatively cold water, and then the water coming back down on the left side with the red arrow, that's the water that's been warmed by the sun. And so you see this water then come down and go into the tank. Now, one thing to be specific here, you would not use the water that's going up to the roof to actually go into the hot water heater and come out of your shower head. Okay, there would be a heat exchanger inside of the water heater to keep the water that collects heat from the sun separate from the what's called domestic hot water, the water that's in the tank that will actually come out, and you can use it to, you know, wash your dishes, wash your clothes, bathe in, whatever. Okay, so there are actually two heat exchangers. One's on the roof collecting energy from the sun, and the other heat exchanger would be in the tank. But notice that those two heat exchangers, their purpose is to actually encourage energy transfer between the sun and the system, and we would probably take the system in this case to be all of the water inside of these collection pipes. And of course, the heat exchanger as well in the tank, the hot water tank, is designed to transfer heat to the water, the domestic hot water that's in the tank. Or the domestic water, I guess we're heating it, aren't we? So intentionally here, the system is closed, no mass transfer, this water wouldn't leak out, but heat is encouraged to flow in and out of this water in particular points. Now you might say, well, why is it so important? Why couldn't you just take the domestic hot water, make sure you got good piping so we don't get junk in it, send it up to the roof, bring it back down, heat it, and away we go? There's actually a very good reason. It's winter, right? Winter time. In wintertime, you don't want to have to drain this system. You probably won't get a whole lot of heat from the sun, so you need some other backup, but you don't want to disassemble this structure, right, or this system, and I should say this device, because the system is the water inside the pipes. But you don't want to deconstruct it, so you need antifreeze in it. Well, do you want to add antifreeze all the time to your water that's coming in? Do you want to bathe in antifreeze? Probably not, right? So there's a really practical reason for having this as a closed system rather than the next type, which is actually an open system. Now, I don't know if you'll recognize this item on the left, but it's an underwater jet engine, which is really interesting. It's made for, or it's designed for driving whatever would, you know, a ship that has this underwater, or even a submarine could use this. The way it works is steam comes in and expands, causing entering water to expand also, and then a high pressure jet comes out the backside. Now, if we wanted to study this, what would we take as the system? Well, the interesting part to me looks like the water coming in, the water leaving, and the steam and air that are injected as well. So sort of a revolved shape inside of that engine, right, where the water comes in and leaves that primary area. Now, this is an open system because both mass and energy are allowed to cross the system boundary. Let's take a couple more examples. Here's the Thermos, and as I said, it's isolated because neither mass nor energy should cross the system boundary. Here's a nice car to have, right? And if you roll up the windows in the summertime, it's probably a bad idea. You really want the heat to leave that car. And it will to some extent, but I'd suggest if you have a car quite as nice as this that you roll down the windows a little bit, if you can, to allow energy to easily leave being carried by mass. But in this case, we've got the car sitting out in the summertime, the windows are rolled up, so essentially no mass crosses the boundary between the interior of the car and the outdoors, but energy can certainly transfer over. And so what typically happens in this case is the sun beams down on the car, transferring energy into the car, warms up the interior, cracks the dashboard. Now you got to work on the dashboard, right? I don't know why. It seems like more recent cars don't have the trouble of cracking dashes like this more classic car has. But anyway, if you have a nice car like that, take care of it, please. Open systems. If you've ever seen this, this is a cross-section of a carburetor's Venturi, and the design of the Venturi is such that air comes in on one side, it leaves on the other. There's a Venturi tube over there on the right in sort of schematic cross-section view. But you notice that as it goes along, it necks down. The purpose of that is to reduce the pressure. Later on in the course, we'll see how that works. It actually has to do with energy conservation, but you may know it as Bernoulli's equation or principle. But anyway, as the air comes in and it necks down, the pressure in the air drops, and that way it can actually suck fuel into the airstream. And that's the old way that fuel was metered into an engine or added to the air in precise amounts. Now, if you think about the interesting part here, the Venturi itself is fairly interesting. We could draw a system boundary around it. Obviously, some of the boundaries would be real, some of them would be imaginary at either end of the Venturi. But both mass and energy would be allowed to cross that system boundary. So that's an example of an open system.